Welcome, it's Paul. This script is designed to show you how you can use the built-in functions in R for the binomial and Poisson distributions to start analyzing some real-world data. And I'm also going to try to show you why the chi-squared test that you were using blindly in earlier scripts might do some of the work that would also be done by a permutation test. Let's start with the binomial distribution, and let's think of baseball as a model. You're a baseball manager, and your scout says, this rookie's a 300 hitter, meaning, I think when this rookie goes to the plate, the probability is 30% that he'll get a hit. Well, you're a month into the season. This rookie's been at bat 100 times. He has only 26 hits. He's batting .360. And the question is, should you fire your scout? The scout said this is a 300 hitter, and it looks like he's a 260 hitter. Well, the quick way to answer that question is to ask, what is the probability that if you have a binomial distribution with 100 trials, each with a probability of 0.3 or success, that the number of successes will be less than or equal to 26. And what we learn is that that will happen 22.5% of the time. So even if the rookie really is a born 300 hitter, what you observe could happen more than 20% of the time, not a good basis for firing your scout. Of course, if you want to present this to the uninitiated, a picture is worth 1,000 words. Here is a bar plot of the binomial distribution. I have shown in blue the situation where a 300 hitter gets more than 26 hits. I've shown in red the situations where he gets less than 26 hits. And you say, our actual observations are right there. There's no basis for ruling out the hypothesis of a 300 hitter. Now, here's a standard way of comparing observed and expected values. It's the chi-squared function that leads to the chi-squared distribution. It takes a vector of observations. It takes a vector of expected values. And what you do is, for each observation, you subtract off the expected value of that observation, you square the result, and then you rescale by dividing by the expected value. So, in our case, we might make 5 observations of a binomial random variable, each with an expected value of 100. And for observations, we can take samples from a binomial distribution, 1,000 trials, probability 0.1 of success. That will give us an expectation of 100 successes. And here's what the vector looks like. This is just simulating what would happen if you had a situation where you were expecting 100 successes, but the actual number of successes came from a binomial distribution. And this chi-squared function that we've just written will come up with a numerical value of the discrepancy. Here it computed 9.22. The larger the value, the larger the discrepancy on the average. With permutation tests as an inspiration, you can see how you might now be able to assess this number. You say, let's try this 10,000 times. 10,000 times, we will draw 5 samples from a binomial distribution with an expected number of successes equal to 100, compute the value of our chi-squared function, and store it in the vector CS. We do that. We display the histogram, and you say, that's a pretty shade of pale blue. Well, it's a very clever pale blue. I use 0 red, 0 green, 1 blue, but I made it transparent by saying I only want 1/4 for this color. If I do the same thing with 10,000 trials, but the probability of success down to 0.01, the expected number of successes is again 100. And if I do the same thing, the histogram looks very much the same. How did I overlay those? Well, the second histogram was red, but it was transparent red, so that when we have blue but no red, we see it there. When we have red but no blue, we see it there. And when we have both red and blue, we see it here. This is similar to the technique for displaying two bar plots side by side, but here you can do it by overlaying the histograms. Now, maybe you're already thinking, the limit of a binomial distribution is a Poisson distribution. I bet you if I drew samples from a Poisson distribution with a parameter of 100, that's lambda equals n times p, I get roughly the same distribution as chi-squared values. And sure enough, when I do a third distribution, the histogram looks much the same. This is how classical statistics works. If you don't have a computer that'll do the computation 10,000 times, because, say, you're living in the 1920s, what you do is come up with a mathematical model to simulate the result of carrying out an experiment 10,000 times. And for reasons that will become apparent in another 2 or 3 weeks, there is a continuous probability distribution called the chi-squared distribution that matches up beautifully with these histograms. For those of you who've heard of the normal distribution, the way I make this chi-squared distribution is I generate 5 samples from a normal distribution and then sum up their squares. Now we've got a way of assessing the discrepancy of a specific observation. I always like to do this with a fabricated sample the first time, and then once I know it's working, I use it on real-world data. So, I've drawn 5 samples from a Poisson distribution. R in front of Poisson means give me random samples, and let's save the value that the chi-squared function computes from that. Now we've got our histogram from having done this 10,000 times, and I can ask what is the mean value of a function that equals 1 for all the trials where the histogram gave a larger value for chi-squared, and that came out to be 0.65. Say, yeah, if this can arise by chance 65% of the time, I don't think there's anything special about my observation, and that's quite reasonable since my observation was drawn by the same process that constructed the histogram. If you ask what's the probability that the p chi-squared distribution function with 5 degrees of freedom gives same value, you get something that's very, very close to what you got from the histogram. Now there's a catch here. This is nicely explained in the Chihara and Hesterberg textbook, and now that I know this is available electronically for free through the Harvard Library System, I'm just going to encourage you to read the details there. But the rule is, if you use observations to estimate a parameter, then you have to cut down the number of degrees of freedom by 1 for each estimated parameter. A real-world example. In the real-world example, you generally don't know the mean of the population. All you can do is estimate it by averaging together your samples. So, if I have nothing but this one sample V, the best I can do is to say, for my expected values, I will repeat it 5 times. Here the repeated value came out to 99.6, but the last time I ran this while practicing for this video, it came down around 95. Okay, so we're going to try our 10,000 times again. But in this case, every time we make an observation, we're going to get the expected value by taking the mean of those 5 samples. And there's the histogram. Suppose I didn't acknowledge the fact that I used the data to get the expected value. And I said, oh, I've got 5 observations, 5 degrees of freedom. Then the graph of the chi-squared function would not match very carefully. And the reason is that because I was using the expected value computed by averaging the 5 values instead of the true population mean of 100, I'm going to cut down on the expected discrepancy. If I drop the number of degrees of freedom by 1, then I get a remarkably good fit. A lot of people just learn this as a rule of thumb. I'll come back to this again and again, and maybe a month from now you'll start feeling more comfortable with the chi-squared distribution. If you want to display our observation, the AB line function with v equals chi-save draws a nice vertical line at the position of the saved value. There it's shown in blue, and you can say, here's the discrepancy that we got from our actual observations, and look, when we did a simulation or simulated the result of that simulation by using the built-in chi-squared function, a lot of times we'd see an even greater discrepancy. So to summarize, we've got 3 ways of estimating the probability that a deviation from uniform could arise by chance. One way is you can compare with a histogram and say 72% of the values shown in this histogram are larger than the observed discrepancy. Or you can use the chi-squared function, which also says 71% of the area under the graph of that function is to the right of my observation. Or you can use the built-in chi-squared test and get a p-value of 0.714. Any of these is valid. I would say the first one, where I actually draw the histogram, shows most clearly what you're doing in order to carry out your analysis. The final one looks the most official and gives you the least insight into why the test works. Now let me show you some examples with real-world data. These are taken from Chihara and Hesterberg's mathematical statistics with R and resampling, which I credit for about 90% of what I know about statistics. Here's a vector that has a table of the quarter of the year in which athletes were born. And the funny thing about this is there are surprisingly few athletes who were born in the period May, June, and July. Question, is this discrepancy significant? Well, let's assess this in various ways. We can just pass these observations into the built-in chi-squared test. It will compute the expected values and compare with a chi-squared distribution for the right number of degrees of freedom. And it says the p-value is 0.01. The probability that this large a discrepancy from uniformity would arise by chance is only a little bit bigger than 1%. It actually looks kind of significant. Another way, we can use our own chi-squared function. We can use our chi-squared function to compare with the expected value and ask, what is the probability that the built-in chi-square function with 3 degrees of freedom will give a value greater than that. Lower dot tail always computes the probability for greater than rather than less than or equal to. And what do you know? We get 0.0118, the same number. The third approach is we can do a simulation. We make a vector with 4 elements, and then over and over again we sample from that, take the sum of the observations, and from our simulated observations and the expected value in each quarter, if these were uniformly distributed, we calculate the chi-squared function. We plot a histogram of the result. We show the actual data on the histogram with a vertical line, and we compute the fraction of the time that the histogram shows a greater value for the chi-square statistic. And that again is 0.01 and change. In fact, looking at the area under the graph of the chi-squared density function, excuse me, gives the same number. So, while it's nice to do the histogram, it shows you what's going on. In this case, the built-in chi-squared function really gets you the same number much more quickly. Now let's do a sports example. Are home runs independent events? Is there just some small probability every time someone goes to the plate that a home run is going to become the outcome? If that's so, the number of home runs per game should have a Poisson distribution. Well, we can check this with data from the Philadelphia Phillies in 2009. Here's our CSV file converted into a data frame, and we have the outcome of the game, the number of hits, the number of doubles, and so on. But all that we're concerned with is the number of home runs. If we want to model this with the Poisson distribution, we need the parameter for the distribution. And since we know that the expectation of a Poisson distribution is equal to its parameter, what we do is take the mean number of home runs per game and say we're going to model with a Poisson distribution with parameter 1.3827. That means we've estimated one parameter. If we do chi-square, we have to subtract 1 from the number of degrees of freedom. Well, we make a table from Phil's $ home runs. It looks like this, and I don't like that 5 there. You're not supposed to do chi-squared tests when the expected number of values is too small. 9 is actually pushing it for too small. So let's, as the 5th entry in our table, have 4 or more home runs. Let's combine the 4 and 5 results. It took me a while to figure out exactly how to do this in R, but there are the successful results. And now what are we going to do? We're going to compute the expected counts for 0, 1, 2, 3, and more than 3 home runs, assuming that the number of home runs in the game is given by a Poisson distribution. So here's expected. We take 162, the number of games in the season, times the probability for values 0 through 3 of a Poisson distribution with parameter lambda. And then the 5th value is going to be 1 minus the probability of getting less than or equal to 3 home runs. If you look at Chihara and Hesterberg online, you'll see the observed and expected values as the top and bottom rows of their table. I think it's 3.10. Okay, we use our own chi-squared function to assess this discrepancy. we get a mysterious value 0.83, and now we have to interpret it. We estimated one parameter from the data, so there are only 3 degrees of freedom. And one way we can do this is to use our chi-squared function and the built-in function for the distribution function of the chi-squared distribution. That gives a p-value of 0.84. It says we actually have a very high probability of exceeding this discrepancy if we just generate from the Poisson distribution. This result really does not look significant. A second approach is we can simulate a 162 game season 10,000 times, generate home runs from the Poisson distribution, sum up the number of occurrences of 1, 2, 3, 4, or of 0, 1, 2, 3, or 4 or more home runs, and then use our chi-squared function to compare the actual count of home runs with the expected count, make a distribution of the result, compare it with the chi-squared function, and here we don't have this beautiful fit. Why? This is real-world data, and there are actually reasons to believe that the Poisson model is not that good in this case. There are pitchers who are notorious for serving up gopher balls, for giving up a lot of home runs, and the probability of a home run is not really constant from batter to batter. Nonetheless, I can compare the result with this histogram, and again, I reach the same conclusion. This result could have arisen by chance from our model with a very high probability. In this case, my opinion, as a believer in non-parametric methods, is that the simulation is a better approach. Using the built-in chi-squared test is suspect, partly because I'm not really sure the Poisson model is that good, but probably more importantly because the number of home runs is on the small side. You'll get a chance on the homework to do this sort of simulation with the original chi-squared test, which involved the number of deaths resulting from horse kicks in Prussian cavalry corps. And that ends this little video.